The drilling head screamed as it met resistance 3 kilometers beneath the Antarctic ice. Not the soft, predictable resistance of compacted snow or ancient glacial ice, but a sudden metallic vibration transmitted through the drill string, up through steel, and into the hands of the technicians standing on a platform surrounded by endless white. The sound was wrong. It was sharp, rhythmic, too regular to be stone fractured by pressure alone. When the drill was withdrawn, its cutting edge came back scarred, not chipped, but abraded in a pattern that suggested contact with something flat, dense, and deliberately shaped. At that depth, beneath ice laid down long before the last glacial maximum, beneath pressure that crushes mountains into memory, there should have been nothing but bedrock smoothed by slow geological violence. Yet the data feed told another story. The resistance spike formed a clean plateau. The radar echo showed an angle where angles should not exist. Antarctica does not offer itself easily. Conceals, compresses, it erases. The continent is not merely covered by ice. It is actively rewritten by it. Each snowfall becomes a page. Each glacial advance a chapter that presses the previous one thinner, blurring ink into suggestion. And yet, sometimes the pressure preserves instead of destroys. Sometimes, beneath kilometers of frozen time, shapes remain intact, waiting in silence far older than any human language. The anomaly was catalogued, logged, and provisionally dismissed. Instrument error, perhaps, a misreading caused by bedrock heterogeneity. The official report would later describe it as a localized density irregularity consistent with subglacial geological variation. The phrase sounded calm, reassuring. It carried the authority of peer review and statistical smoothing. But among the engineers and glaciologists present that day, the memory lingered. The vibration had not been random. The resistance had not behaved like fractured granite or metamorphic schist. It had responded like a surface. Antarctica has a way of doing that, of introducing doubt not through spectacle, but through subtle deviations from expectation. A flatness where curvature should dominate. A symmetry buried where chaos reigns. These deviations are not new. They have been recorded since the first systematic surveys of the continent, when early radar flights traced shapes beneath the ice that resembled river valleys, mountain ranges, and coastal plains. Antarctica was not always frozen. Stratigraphic analysis places large portions of the continent in temperate latitudes during the late Mesozoic and early Cenozoic eras. Fossilized pollen trapped in sediment cores speaks of forests, ferns, slow-moving rivers cutting into soft rock under skies unburdened by ice. But the anomaly beneath the drill was not a river channel. It was not a ridge. Its geometry resisted easy classification, and it forced an uncomfortable thought into the periphery of scientific consideration, that something beneath Antarctica might not be natural at all. The stakes of such a possibility are immense, not because they promise revelation, but because they threaten erasure. Earth is an efficient destroyer of its own past. Subduction zones recycle crust into the mantle. Sea levels rise and drown coastlines beneath sediment and salt. Glacial advances grind cities into dust and scatter their remains across continents. If an advanced civilization had existed before the end of the Pleistocene, its coastal centers would now lie beneath hundreds of meters of ocean. Its inland structures would have been crushed, buried, or chemically altered beyond recognition. Antarctica, paradoxically, may be the one place where such remnants could survive, not despite the ice, but because of it. The Antarctic ice sheet began its major expansion roughly 34 million years ago, at the Eocene-Oligocene boundary. Since then, it has grown, retreated, and grown again, responding to orbital cycles, atmospheric composition, and tectonic shifts. Each advance sealed the surface beneath it, locking landscapes in cryogenic suspension. Unlike erosion by wind or water, ice can preserve as much as it destroys. Organic material, stone alignments, even voids can remain intact beneath stable ice for millions of years. And yet, Antarctica is also one of the least accessible places on Earth. Less than 2% of its bedrock has been directly sampled. Most of what is known comes from indirect methods: radar tomography, gravitational mapping, seismic reflection. These tools are powerful, but they are interpretive. They translate echoes into models, probabilities into images. When those images show something unexpected, the tendency is not to rewrite history, but to adjust the interpretation until it fits existing frameworks. The first site to challenge those frameworks lies beneath East Antarctica, in a region known as Aurora Subglacial Basin. Radar surveys conducted over decades revealed an anomalous formation designated ASB-17. According to the data, it is a rectilinear structure measuring approximately 1,200 meters in length, 800 meters in width, and rising nearly 90 meters above the surrounding bedrock. Its material density differs sharply from the basaltic substrate around it. The edges appear straight, the corners sharply defined. It sits on a plateau that itself shows signs of artificial leveling. The paradox is immediate. The basin was last ice-free more than 15 million years ago. At that time, according to conventional models, hominins had not yet developed beyond primitive arboreal forms in Africa. Stone tools would not appear for millions of years. Architecture of this scale should not exist. Mainstream explanations suggest ASB-17 is a tabular intrusion of igneous rock, perhaps a laccolith formed by magma forcing its way between sedimentary layers. The straight edges, they argue, are artifacts of radar resolution and data interpolation. But laccoliths do not form perfect rectangles. Their margins are irregular, responding to fractures and pressure gradients. Mathematical modeling of magma flow under known Antarctic conditions fails to produce the observed geometry. Furthermore, seismic reflections from ASB-17 show internal voids, negative spaces inconsistent with solidified magma. These voids are arranged in repeating intervals, suggesting chambers or corridors rather than random gas pockets. The skeptic's view leans heavily on probability. Nature, given enough time and complexity, can produce shapes that mimic intention. But probability cuts both ways. The likelihood of such regularity occurring once might be dismissed, but ASB-17 is not alone. A second anomaly lies beneath the Transantarctic Mountains, where a subglacial canyon known as the Shackleton Trough reveals a series of stepped terraces carved into its walls. Each terrace is precisely 5 meters in height. The spacing is uniform. The surfaces are smooth, bearing striations that run perpendicular to glacial flow. Geological consensus attributes these terraces to differential erosion, where layers of varying hardness wear away at different rates. Yet core samples extracted from these terraces show homogeneous rock composition throughout. There is no stratigraphic justification for stepped erosion. The striations, when examined microscopically, show signs of tool-like abrasion rather than glacial scouring. Their orientation does not align with known ice movement vectors during any glacial phase. To dismiss this, the explanation shifts again. Post-glacial fracturing, freeze-thaw cycles, unknown localized stress patterns. Each explanation addresses part of the anomaly, but none account for the totality. The terraces are too regular, too deliberate, and they extend for nearly 7 kilometers along the canyon wall. The third site emerges not from radar, but from gravity. Satellite-based gravimetric surveys over Wilkes Land revealed a mass concentration anomaly, a dense object buried beneath ice and sediment, exerting a gravitational pull inconsistent with surrounding geology. Initially theorized as an impact crater, the anomaly measures nearly 500 kilometers in diameter. but impact modeling fails to account for the absence of ejecta. There is no corresponding debris field, no shocked quartz, no iridium spike in nearby sediment cores. Closer analysis reveals a central structure within the anomaly, a circular formation approximately 30 kilometers across, with a raised rim and a flattened interior. The density profile suggests composite materials rather than uniform rock. The skeptic's explanation proposes mantle plume activity or an ancient volcanic caldera. But calderas collapse inward. This structure does not. Its rim is reinforced. Its interior shows layered density gradients that suggest construction rather than collapse. If this were a single anomaly, it might be ignored. 2. Debated. 3. Reconsidered. But Antarctica offers more. The fourth site lies near the geographic South Pole, where ice flow models predict smooth basal topography. Instead, radar reveals a network of linear features intersecting at right angles beneath the ice. The grid spans approximately 40 kilometers by 40 kilometers. Each line is consistent in width and depth. They intersect at regular intervals. No known geological process produces orthogonal networks at this scale beneath continental ice. The mainstream view attributes the grid to subglacial meltwater channels. But meltwater follows gradients. It meanders. It branches. It does not form perfect right angles. Hydraulic modeling shows that water under ice pressure seeks the path of least resistance, not geometric precision. To produce such a grid would require constraints not present in natural systems. At this point, skepticism becomes a form of inertia. The refusal to consider an alternative timeline not because it lacks evidence, but because its implications are destabilizing. To accept that Antarctica may hide remnants of Earth's first civilization is to accept that human history is not a straight line, but a series of rises and collapses punctuated by catastrophic resets. The unifying theory emerges not from speculation, but from synthesis. During the late Pliocene, before the full establishment of Antarctic ice sheets, global sea levels were significantly lower. Continental shelves were exposed. Climate zones were different. Antarctica, positioned farther north due to plate tectonics, supported tempered environments along its coasts. In this window, a technologically advanced civilization could have emerged, utilizing coastal plains and river systems now buried beneath ice. Their architecture, built from stone and composite materials, would have been vulnerable to erosion everywhere else on Earth. But in Antarctica, the rapid onset of glaciation would have sealed it away. As ice advanced, it would not have immediately destroyed all structures. Instead, it would have buried them, freezing them in place. Over millions of years, the weight of ice would compress, but also protect. Unlike tectonically active regions, much of Antarctica's interior is stable. No major subduction, minimal seismic activity, perfect vault. The geological record supports abrupt climate transitions. The onset of Antarctic glaciation was rapid. Within a few million years, temperatures dropped, ice expanded, and ecosystems collapsed. A civilization unprepared for such a shift would have been erased not by war or decline, but by climate itself. The relevance of this possibility extends beyond curiosity. Modern civilization, too, builds along coasts, too assumes stability. Antarctica becomes a mirror held up to the present, reflecting a future where ice or sea reclaims what was thought permanent. The lesson is not one of doom, but of humility. Earth has reset itself before. It will do so again. As research continues, the ice remains indifferent. It does not reveal willingly. Each anomaly must be coaxed from beneath kilometers of pressure and cold. The drill that struck resistance is silent now, its scarred edge cataloged and stored. But beneath the white silence, the shapes remain, waiting. The waiting beneath Antarctica is not passive. It is not the stillness of abandonment, but the stillness of compression. Ice does not sleep. It moves millimeter by millimeter, grinding continents into equations of pressure and flow. And yet, within that movement, there are zones of relative calm, subglacial plateaus where ice has slid evenly for millions of years, preserving what lies beneath like a hand held steady over a wound. It is in these zones that the next layer of the investigation begins. One such zone lies beneath what appears, from above, to be an unremarkable stretch of polar plateau. The surface offers no hint of what lies below. No crevasses, no mountain shadows, only wind-polished snow stretched to the horizon. But radar tomography reveals a buried basin filled not with sediment, but with a material whose dielectric properties do not match any known Antarctic bedrock. The basin is oval, approximately 18 kilometers long, and sealed beneath nearly 4 kilometers of ice. It has been designated internally as Site E12. Core samples extracted from the uppermost layers of the basin reveal something unexpected: a stratified sequence of crushed stone, compacted ash, and metallic particulates embedded within a cement-like matrix. This is not sediment laid down by water or ice. The grain size distribution is uniform. The angularity of the fragments suggests mechanical crushing rather than natural weathering. Trace analysis identifies alloys containing copper, tin, and trace elements not typically associated with volcanic output in this region. The paradox deepens when radiometric dating is applied. The matrix binds materials of different ages together. Some fragments date back over 20 million years. Others appear significantly younger, clustered around a window between 3 and 5 million years ago. Geological processes do not mix time this way without leaving signatures of disturbance. Faulting, intrusion, melting. None are present. The layers are orderly, intentional. The skeptic's view proposes contamination, drilling artifacts, human error introduced during extraction. But the metallic particulates are embedded within the matrix at depths untouched by the drill bit. Their distribution follows a repeating pattern, suggesting layering rather than random inclusion. When the matrix is subjected to microstructural analysis, it reveals a crystalline alignment consistent with slow curing under controlled conditions. Nature cures chaotically. This material did not. To understand how such a structure could exist, it becomes necessary to step back, far back into deep time, into the shifting geometry of continents and currents. Antarctica has not always been isolated by the circumpolar current that now locks it in ice. That current formed only after the opening of the Drake Passage, roughly 34 million years ago. Before that, warm equatorial waters reached Antarctic shores. The continent was green at its edges. Rivers carried sediment from inland highlands to coastal plains. These plains, now buried, would have been ideal for settlement. But settlement alone does not explain advanced engineering. For that, energy is required. The next anomaly provides a clue. Beneath the Gamburtsev subglacial mountains, a range entirely hidden beneath ice, seismic surveys detect a network of voids and conduits extending downward into the crust. These are not volcanic tubes. Their walls are smooth. Their diameters are consistent, averaging 12 meters. They descend in spiraling paths, converging toward a central chamber nearly 2 kilometers below the bedrock surface. The chamber itself is spherical, with a diameter of approximately 300 meters. The paradox is absolute. Spherical chambers of this scale do not form naturally within continental crust. Even magma chambers are irregular, shaped by pressure gradients and fractures. This chamber's geometry suggests deliberate excavation. The skeptic's explanation again invokes volcanic activity, specifically a collapsed magma reservoir later reshaped by tectonic stress. But stress deforms. It elongates. It fractures. It does not perfect. Geochemical analysis of gases trapped within the chamber walls reveals elevated levels of noble gases, particularly helium-3, an isotope rare on Earth but associated with mantle processes and, more intriguingly, advanced energy research in modern times. The concentration is too high to be explained by passive diffusion alone. Something harvested it or contained it. If the chamber functioned as an energy node, drawing geothermal heat or mantle-derived materials, it would explain the presence of advanced construction elsewhere. Energy enables permanence. It allows stone to be cut, metals to be alloyed, materials to be transported across distances that would otherwise limit early societies. The emerging picture is not of a scattered, primitive culture, but of a centralized civilization capable of large-scale planning. One that understood geology not as an adversary, but as a resource. Further north, beneath the now submerged continental shelf off Antarctica's ancient coastline, seismic reflection reveals another structure. A terraced complex rising from the seafloor like a stepped pyramid laid on its side. Each terrace is precisely aligned with cardinal directions as reconstructed for the Pliocene epoch. The terraces are built from blocks averaging 4 meters in length, interlocked without mortar. The structure spans nearly 6 kilometers. The skeptic's explanation suggests a drowned continental slope shaped by landslides. But landslides do not align with cardinal directions. They do not produce uniform block sizes, nor do they stack blocks in load-bearing configurations that distribute weight evenly across terraces. Finite element analysis of the structure's geometry reveals intentional stress distribution, an understanding of mechanics beyond trial and error. Why build here, at the edge of a continent destined for ice? The answer may lie in timing. Climate proxies indicate that the late Pliocene experienced oscillations, periods of warming followed by abrupt cooling. A civilization attuned to these changes may have sought refuge inland, moving critical infrastructure beneath ground, beneath ice, beneath the reach of surface chaos. The Antarctic ice sheet becomes, in this context, not merely a destroyer, but an unintended archivist. The investigation cycles again, this time focusing on biological anomalies. Beneath Lake Vostok, one of Antarctica's largest subglacial lakes, water samples retrieved from accretion ice contain complex organic molecules arranged in repeating sequences. These are not DNA, but they exhibit a modularity suggestive of engineered biochemistry. The lake has been isolated from the surface for at least 15 million years. Any biological input must predate that isolation. Mainstream interpretation frames these molecules as extremophile adaptations, life finding a way in isolation. But extremophiles adapt randomly. Their molecular structures vary. These sequences do not. They repeat with precision. They resemble storage rather than metabolism, information rather than survival. The possibility emerges that Lake Vostok was not merely a lake, but a repository. Water, sealed beneath ice, stable in temperature and chemistry, becomes an ideal medium for preservation. If information were encoded biologically, using molecular structures resistant to decay, it could survive where stone might crack and metal corrode. At this stage, the pattern is undeniable. Structures beneath ice, energy systems beneath mountains, materials that defy geological categorization, information preserved in isolation. The skeptic's view fragments the picture, addressing each anomaly separately. But fragmentation is itself a bias. When data points align across disciplines, geology, chemistry, physics, biology, the responsible approach is integration. The unifying theory solidifies. An advanced civilization arose during a climatic window when Antarctica was habitable. It developed technologies suited to long-term stability rather than expansion. Anticipating environmental collapse, whether through observation or inherited knowledge, it built downward, not upward. When ice came, it retreated beneath it, sealing its legacy away. The collapse, when it arrived, was not sudden. It was attritional. As temperatures dropped and ice advanced, surface populations dwindled. Energy systems failed or were deliberately shut down. Knowledge was stored, not transmitted. Survival gave way to preservation. Why no direct evidence on other continents? Because Antarctica was the vault, not the center. Coastal cities elsewhere were erased by rising seas at the Pleistocene boundary. Inland sites were ground down by glaciers or reclaimed by forests and deserts. Only Antarctica, locked in ice early and kept stable, retained its buried past. The modern relevance of this realization is quiet but profound. Civilization measures success by growth, by visibility, by monuments that rise into the sky. But endurance may require the opposite. To last is to hide, to align with geological time rather than human time. Antarctica teaches that what survives is not what dominates the surface, but what harmonizes with deep processes. Today, as ice shelves fracture and subglacial lakes awaken, fragments of that buried past may surface, not as grand revelations, but as subtle anomalies in data streams. A vibration in a drill, a density spike in a gravity map, a molecule out of place. The forgotten Earth is not forgotten because it is gone. It is forgotten because it is buried, compressed beneath assumptions as thick as ice. To listen for it requires patience and a willingness to accept that human history may be far older and far more fragile than the surface suggests. And so the work continues, slow as ice flow, deliberate as deep time. Beneath Antarctica, the silence holds. But silence in geology is never empty. The silence beneath Antarctica is layered. It is not a single absence of sound, but a stack of muted histories pressed together under pressure measured in megapascals and millennia. To understand what may lie there, one must slow the mind to the speed of ice itself, to a pace where change is registered not in years or centuries, but in isotopic ratios and mineral transformations. Only then does the next phase of the story begin to take shape, not as a revelation, but as an accumulation. Far beneath the West Antarctic ice sheet, in a region long considered geologically unstable, seismic instruments began to record something unexpected. Not earthquakes, not the low-frequency tremors associated with basal ice movement, but repeating microvibrations occurring at precise intervals. Each pulse lasted exactly 14 seconds. Each was separated by a pause of precisely 180 seconds. The pattern repeated continuously for weeks before gradually fading. These signals were first dismissed as instrumental resonance. Polar environments are notorious for interfering with sensitive equipment. Temperature gradients cause expansion and contraction. Wind induces harmonic noise. Yet when the data were cross-referenced with independent stations spread across hundreds of kilometers, the pattern remained coherent. The signals originated from a fixed point approximately 5 kilometers beneath the ice, embedded within crystalline bedrock. Natural processes do not keep time so faithfully. The source region, later designated Node W3, sits at the intersection of several deep crustal faults. In conventional tectonics, such intersections are zones of chaos, fracturing, fluid migration, stress release. But Node W3 shows the opposite. Seismic waves slow as they pass through it, as though encountering a material that absorbs vibration rather than transmitting it. The attenuation profile resembles that of engineered damping systems used in modern infrastructure to reduce resonance. Core drilling into the periphery of the node retrieves material unlike anything previously cataloged in Antarctic geology. The rock is metamorphic in origin, but exhibits a laminated internal structure, with alternating layers of crystalline silicate and a carbon-rich composite. The layers are uniform in thickness, averaging 3 centimeters each, repeating over hundreds of meters. There is no known geological mechanism that produces such regularity at this scale. Radiometric dating places the formation of the host rock at over 1 billion years old. But the laminated structure is far younger. Thermoluminescence dating of the composite layers suggests an age of approximately 4 million years. This implies intervention, modification of ancient rock long after its formation. A civilization not only present, but capable of reshaping deep crustal material. The skeptic's explanation invokes metasomatism, a process by which fluids alter rock composition over time. But metasomatism follows fractures. It diffuses. It does not produce sharp boundaries between layers, nor does it repeat with mechanical precision. Chemical gradients in metasomatic zones blur. Here they are abrupt. The pulses recorded by the seismometers, when analyzed spectrally, reveal harmonics consistent with resonance within a hollow structure. Cavity, not a void left by dissolution or magma withdrawal, but a chamber with defined boundaries. Modeling suggests a shape elongated along a north-south axis, approximately 2 kilometers in length and 600 meters in diameter. Why would such a chamber exist so deep beneath the ice? The answer may lie in the nature of ice itself. Ice is not merely frozen water. It is a dynamic load, exerting pressure that increases predictably with depth. At 4 kilometers thickness, the pressure exceeds 35 megapascals. Any structure built beneath such a load must be designed to endure it. The laminated damping material at node W3 appears to serve precisely that function, absorbing stress, redistributing force, preventing collapse. This implies foresight, not adaptation after the fact, but anticipation of glaciation before it reached its maximum extent. Climate models indicate that Antarctic glaciation was not instantaneous. It advanced in stages, responding to orbital forcing cycles known as Milankovitch rhythms. A civilization attentive to long-term climate patterns could have observed cooling trends, shifting vegetation zones, expanding seasonal snow. Over generations, these signs would coalesce into a realization. The ice was coming, and it would not leave for a very long time. Such a realization would change priorities. Expansion would cease. Monumentality would give way to endurance. Knowledge would need to be stored in forms resilient to pressure, cold, and time. Stone tablets crack. Metals corrode. Digital storage requires energy. What remains? The answer may be found in the next anomaly, one that exists not as a structure, but as an absence. Beneath a region of East Antarctica known for its thick, stable ice, radar surveys reveal a volume where reflections vanish. Not attenuated, gone. A zone approximately 10 kilometers across where radar waves enter and do not return. The boundaries of the zone are sharply defined, almost spherical. Within it, instruments detect no signal, not even the background noise expected from thermal motion. This is not water. Subglacial lakes reflect radar strongly. This is not rock. Rock scatters. This is something else entirely. The skeptic's explanation suggests saline ice or unusual crystal orientation causing signal absorption. But laboratory simulations of such ice fail to replicate complete signal loss across multiple frequencies. The absorption here is broadband and total. The implication is startling. A material engineered to absorb electromagnetic radiation completely. Perfect sync. Such materials are the subject of modern research, metamaterials designed to cloak objects or absorb energy. To find one beneath Antarctica, embedded millions of years ago, stretches conventional timelines to the breaking point. If this zone functions as an electromagnetic shield, it could protect whatever lies within from external probing. It could also preserve delicate structures from radiation damage over geological timescales. Inside such a shield, information could persist almost indefinitely. This leads to a reconsideration of Lake Vostok and its molecular anomalies. If information were stored biologically, molecular stability would be paramount. Cold, dark, isolated environments slow chemical reactions. Encapsulation within ice and shielding from radiation would further extend longevity. Antarctica offers all of this naturally, if one knows how to use it. The emerging civilization, then, appears not obsessed with conquest or display, but with continuity. Its greatest achievement may not have been what it built on the surface, but what it hid beneath it. As this picture forms, the question of origin becomes unavoidable. Where did such a civilization come from? The temptation is to look outward, to imagine extraterrestrial intervention. But the evidence does not require it. Everything observed can be achieved with materials and energy sources available on Earth, given sufficient time and knowledge. The technologies implied: geothermal energy, composite materials, molecular storage are advanced, but not beyond physical law. The key variable is time. Human history, as conventionally understood, compresses development into a narrow window. Agriculture at 10,000 years, cities at 5,000, industry at 200. But this narrative assumes a single rise from simplicity to complexity. It leaves little room for prior cycles. Yet geology is cyclical. Climate is cyclical. Even biology advances in bursts punctuated by extinction. There is no a priori reason civilization should be exempt. If an earlier civilization arose millions of years ago, it would have faced challenges different from those of today. Lower atmospheric oxygen, different flora and fauna. But it would also have had time to observe, to experiment, to fail, to refine. 1,000,000 years is an eternity for cultural evolution. The absence of surface artifacts from such a civilization is often cited as definitive proof against its existence. But absence is not evidence when erasure mechanisms are overwhelming. Consider the rate of sedimentation on continental shelves. A city built at sea level 5 million years ago would now lie beneath hundreds of meters of sediment, compacted into rock. Its shapes would be distorted, its materials chemically altered. Without targeted investigation, it would be indistinguishable from natural formations. Antarctica, again, is different. Its ice halted surface processes early. It froze landscapes in place before they could be recycled by plate tectonics or buried by sediment. What was there remained there, pressed downward but not scattered. This makes Antarctica not a birthplace, but a refuge. A place chosen not for comfort, but for preservation. The investigation now turns inward, toward the philosophical implications of such preservation. If knowledge was stored, what kind of knowledge was it? Practical, scientific, cultural, or something more fundamental, a warning? The rhythmic pulses from node W3 offer a clue. Their regularity suggests signaling. Not communication in the conventional sense, there is no receiver but a marker. A beacon not meant to be heard by contemporaries, but by those who come later with the tools to detect it. A heartbeat buried in stone, saying not who they were, but that they existed. Why signal at all? Why not simply remain hidden? Because preservation without discovery is oblivion. A civilization that sought continuity would understand that memory requires retrieval. It would design its archives not to be obvious, but to be findable by those capable of understanding them. Too obvious, and they would be destroyed by the unprepared. Too obscure, and they would never be found. Antarctica's extreme environment acts as a filter. Only a technologically capable society can reach its depths. Only one with patience and scientific discipline can interpret its signals. In this way, the ice becomes a gatekeeper. Modern humanity is now at that gate. The warming of the planet, driven by industrial activity, is thinning ice shelves and accelerating basal melt. Subglacial lakes are changing. Ice flow patterns are shifting. Areas long sealed are becoming dynamic. With this change comes risk, not just to climate stability, but to whatever lies beneath. The paradox is stark. The same processes that threaten modern civilization may expose evidence of a prior one. In destabilizing the ice, humanity may unseal the vault. This raises ethical questions rarely discussed. If structures beneath Antarctica exist, should they be excavated, studied, left alone? Disturbance could destroy delicate equilibria maintained for millions of years. On the other hand, continued warming may destroy them anyway. The story, then, is no longer only about the past. It is about the present moment, about a species standing unknowingly at the edge of a much longer narrative. As the ice continues its slow movement, it carries with it stress, heat, and the possibility of revelation. Each creak, each microfracture, each anomalous data point is a reminder that the planet is not static. It remembers differently than humans do, but it remembers all the same. The forgotten Earth is not a metaphor. It is a physical reality, a stratified archive written in pressure and temperature, waiting not for belief, but for attention. And beneath Antarctica, attention is finally arriving. Attention, once focused, changes the nature of what is observed. In Antarctica, attention arrives slowly, measured in Grant cycles, seasonal windows, and the limited reach of machines that must survive temperatures where lubricants seize and metals grow brittle. Each expedition adds fragments, never the whole. And yet, fragments accumulate. Patterns emerge not because anyone set out to find them, but because they refuse to remain isolated. The next layer of the story unfolds not beneath the ice, but within it. Ice cores are among the most precise archives Earth possesses. Each meter represents decades, sometimes centuries, of snowfall compacted into translucent memory. Air bubbles trapped within preserved atmospheres long vanished. Volcanic ash layers mark distant eruptions with chemical fingerprints unique enough to trace across hemispheres. In Antarctica, ice cores descend more than 3 kilometers, reaching back over 800,000 years. Beyond that depth, ice flows and folds, blurring resolution but not erasing signal entirely. Within several deep cores extracted from Dome C and Dome Fuji, researchers identified anomalous particulate layers unlike typical volcanic ash or continental dust. These layers are thin, often less than a millimeter, but persistent across multiple cores separated by hundreds of kilometers. Their composition is unusual. Microspheres of vitrified material containing iron, silicon, and trace rare earth elements in ratios inconsistent with meteoritic input or terrestrial volcanism. At first, these microspheres were attributed to cosmic dust. The steady rain of material Earth accumulates as it moves through space. But cosmic dust distribution is relatively uniform. These layers are not. They appear at specific depths corresponding to narrow time windows clustered around 2 periods. Approximately 3.9 million years ago, and again around 2.6 million years ago, near the onset of the Pleistocene. The microspheres show signs of rapid cooling from extremely high temperatures. Their surfaces are smooth, aerodynamic, suggesting they formed as molten droplets traveling through an atmosphere before solidifying. Volcanic eruptions can produce such spherules, but no corresponding ash layers or sulfate spikes appear in the ice chemistry at those depths. Meteoritic impacts can as well, but no known impact structures of appropriate age and scale exist to account for their global distribution. The skeptic's explanation becomes increasingly narrow. Unknown volcanic events, poorly preserved in the geological record. Yet volcanism leaves signatures beyond ash, gas ratios, isotopic shifts, tephra deposits. These are absent. An alternative interpretation, uncomfortable but increasingly difficult to dismiss, is industrial activity. high-temperature processes that aerosolize molten material into the atmosphere. Processes that operate repeatedly, not as singular catastrophes. If such activity occurred, it implies surface-level operations, factories, energy plants, large-scale manufacturing, during periods when Antarctica's climate was transitioning. But where are the remains of such activity? The answer may lie in the mechanics of ice advance itself. As ice sheets expand, they do not simply cover the land. They scour it. Surface structures are ground down, incorporated into basal debris, and transported laterally before being deposited at the ice margin. Over time, this process obliterates surface evidence while preserving what lies deeper or is intentionally shielded. In several blue ice regions, areas where strong winds ablate surface snow, exposing older ice, researchers have found isolated artifacts embedded within the ice matrix. These objects are small, often no larger than a fist, and initially dismissed as meteorites. But detailed analysis reveals inconsistencies. One such object, recovered from the Allen Hills region, is composed of a nickel-iron alloy with crystalline structures indicative of controlled cooling. Meteoric alloys cool rapidly during atmospheric entry, producing distinctive Widmanstätten patterns. This object does not. Its internal structure suggests slow cooling under regulated conditions. Trace impurities include elements rarely concentrated together naturally. Its surface bears markings, parallel grooves spaced at regular intervals, too fine and uniform to result from random abrasion. The grooves are worn, softened by time and pressure, but their regularity remains detectable under magnification. No known geological process produces such markings on metallic objects. Dating the surrounding ice places the object's incorporation at approximately 1 million years ago. This does not date the object itself, only when it became embedded. Could be far older. The skeptic's response is cautious dismissal. Contamination from modern expeditions. Lost equipment. But the alloy composition does not match any modern industrial standard. And the depth at which it was found, combined with ice flow modeling, makes recent contamination improbable. These findings are not announced with fanfare. They appear in supplementary materials, in footnotes, in conference posters that attract quiet conversations rather than headlines. The scientific community is conservative by necessity. Extraordinary claims require extraordinary evidence. But conservatism, when faced with accumulating anomalies, can become a form of denial. As the data grows, a reframing occurs. Not a declaration, but a subtle shift in how questions are asked. Instead of, could this be artificial? The question becomes, what natural process could realistically produce all of this? The list grows short. At this point, it becomes necessary to reconstruct not just structures, but society. A civilization capable of deep earth engineering, composite materials, atmospheric processing, and long-term planning would require social organization on a scale comparable to or exceeding modern industrial societies. It would need specialized labor, knowledge transmission, governance. It would need reasons to invest enormous resources into preservation rather than expansion. What kind of society chooses to bury its greatest achievements beneath kilometers of ice? One possibility is scarcity, not of resources but of time. Climate proxies indicate that the late Pliocene experienced increasingly unstable conditions. Carbon dioxide levels fluctuated. Ocean currents reorganized. Ice sheets advanced and retreated unpredictably. For a society attuned to environmental feedbacks, these signals would be alarming. Not apocalyptic in a single generation, but inexorable over centuries. Faced with such trends, a civilization might attempt mitigation, geoengineering, atmospheric modification, albedo control. The microsphere layers in ice cores could represent such efforts. High-altitude aerosol injection to reflect solar radiation, a technique debated in modern times, would produce exactly the kind of vitrified particles observed. If such efforts failed or proved insufficient, priorities would shift. Preservation of knowledge becomes paramount, not to save the civilization itself, but to ensure that what it learned is not lost entirely. This reframes Antarctica's role, not a capital, not a colony, but an archive. Archives are built with redundancy, multiple sites, multiple media. That would explain the distributed nature of anomalies across the continent. No single point of failure, no singular lost city, but a network of facilities, each serving a function: energy, storage, signaling, shielding. The rhythmic pulses from node W3 could be part of this redundancy, a low-energy, long-duration signal designed to persist as long as the structure remains intact. Its frequency is low enough to penetrate ice and rock, detectable by seismic instruments that did not exist until recently. It is not a message in language, but a proof of presence. The grid beneath the South Pole could represent a transportation or distribution network, buried intentionally to protect it from surface destruction. The step terraces in the Shackleton Trough could be load management structures, stabilizing canyon walls against glacial stress. The circular formation in Wilkes Land could be a central hub, perhaps partially collapsed, its original purpose obscured by time. Taken together, these elements form a coherent system, not random, not accidental. At this stage, the investigation confronts its greatest obstacle: interpretive bias. Modern humans project their own values onto the past: power, dominance, monumentality. But a civilization that prioritized survival across geological timescales would value invisibility. It would minimize surface expression. It would integrate with planetary processes rather than oppose them. This inversion makes detection difficult. Archaeology, as traditionally practiced, looks for debris fields, for artifacts scattered by daily life. But an advanced society might leave little debris. It might recycle obsessively. It might design materials to degrade harmlessly. Its most important structures would be sealed away, not abandoned. The absence of widespread fossil evidence of such a society's population also demands explanation. Where are the bones? The answer lies in taphonomy, the science of decay. Soft tissues vanish quickly. Bones persist only under specific conditions: rapid burial, low oxygen, minimal disturbance. Antarctica, before glaciation, was biologically active. Scavengers, microbes, weathering would destroy remains. After glaciation, any exposed remains would be ground away by ice. Moreover, a technologically advanced society might cremate its dead, or otherwise dispose of remains in ways that leave minimal fossil trace. Burial practices reflect cultural values. There is no reason to assume they mirror those of early Homo sapiens. As these considerations accumulate, the narrative shifts again. The question is no longer whether Antarctica hides evidence of a prior civilization. The question becomes how much and how intact. This leads to a sobering realization. If such evidence exists, it is not merely historical curiosity. It represents a dataset spanning millions of years, information about climate feedbacks, planetary engineering, societal collapse. Knowledge that could inform humanity's response to its own environmental trajectory. But accessing that knowledge carries risk. Excavation beneath ice sheets can destabilize them. Drilling introduces heat, fluids, contaminants. Even seismic probing alters stress fields. The very act of looking could accelerate loss. Thus emerges the final paradox of the investigation so far. To learn from the past, humanity may have to destroy part of it. This paradox mirrors the one that may have faced the prior civilization. To survive, they altered their planet. In doing so, they may have set in motion forces they could not fully control. Their response, to retreat, to archive, to wait, suggests an acceptance of limits. Modern civilization struggles with that acceptance. As satellites map Antarctica with increasing resolution, as autonomous vehicles traverse subglacial lakes, as machine learning algorithms detect patterns humans might miss, the ice's silence grows thinner. Not because it is speaking louder, but because listening has improved. Every anomaly cataloged adds weight to a story that no longer fits comfortably within existing timelines. A story of rise not once, but more than once. Of intelligence not as a singular event, but as a recurring property of complex systems given enough time. The Forgotten Earth, in this light, is not a cautionary tale carved in stone. It is a living process. Civilizations emerge, transform their environment, confront limits, and either adapt or vanish. The planet records each cycle differently, preserving some traces and erasing others. Antarctica preserves by freezing, by pressing down, by waiting. And waiting, in geological terms, is never passive. Waiting changes the nature of intention. Over long spans of time, purpose itself erodes, leaving behind structures that no longer explain themselves, systems whose original logic must be inferred from scars and residues rather than instruction. Antarctica is full of such residues, but the next phase of the story requires stepping away from individual anomalies and listening instead to the continent as a whole. Its mass, its balance, its slow conversation with the mantle beneath. Antarctica is heavy. The ice sheet weighs trillions of tons, depressing the continental crust beneath it by hundreds of meters. This process, known as isostatic loading, is not uniform. Where ice is thickest, the crust bends more deeply. Where it thins, the crust rebounds. These movements occur over tens of thousands of years, slow enough to feel permanent to human senses, but rapid on geological scales. When scientists began modeling Antarctic isostatic adjustment with increasing precision, something unexpected emerged. The rebound rates in certain regions were anomalously low. Even accounting for mantle viscosity variations, the crust beneath parts of East Antarctica behaved as though it were mechanically reinforced. Not stiffer in the brittle sense, but damped, resistant to flexure in a way that suggested internal support. At first, this was attributed to cratonic stability. East Antarctica is underlain by some of the oldest continental crust on Earth. Ancient shields formed over 3 billion years ago. Such crust is thick, buoyant, and slow to deform. But the spatial correlation did not hold. The damped regions did not align with craton boundaries. Instead, they traced patterns already familiar from radar and seismic anomalies. Beneath the Aurora Basin, near the Gamburtsev Mountains, and along corridors connecting previously identified sites. In other words, the crust was not behaving as a natural body alone. It was behaving as a modified one. Finite element modeling of these regions revealed that the observed deformation patterns could be replicated if large subsurface structures acted as low distribution systems, spreading ice weight laterally rather than allowing it to concentrate. The effect would be to stabilize the ice sheet above, reducing fracturing and basal slip. Such stabilization would be advantageous for preserving whatever lay beneath. The implication is subtle but profound. The subsurface architecture may not only be preserved by the ice, it may be actively shaping how the ice behaves. This shifts the relationship between civilization and environment entirely. Rather than being passive victims of glaciation, the builders may have altered Antarctica's response to ice itself. Not to stop it, but to manage it, to slow its destructive tendencies, to create zones of relative calm where preservation could occur. This idea gains support from the distribution of subglacial lakes. Antarctica contains hundreds of them, bodies of liquid water trapped beneath kilometers of ice by geothermal heat and pressure. Their locations are not random. Many cluster along linear features that correspond to known anomalies. Water follows heat. Heat follows structure. If subsurface systems were designed to channel geothermal energy, they would naturally give rise to stable liquid reservoirs. Lake Vostok is the most famous, but it is not unique. Beneath the Recovery Glacier, beneath Totten Glacier, beneath the Foundation ice stream, similar lakes appear, often elongated, often aligned with subsurface features. Their temperatures are remarkably stable. Their chemistry suggests long-term isolation, but not stagnation. Slow circulation occurs, driven by gradients that remain constant over millions of years. Water is a solvent. It dissolves, transports, reacts, but it is also a medium. If knowledge were stored chemically, if structures required minimal maintenance, water would be an ideal environment, shielded from radiation, buffered from temperature extremes, chemically predictable. The idea of Antarctica as an engineered cryogenic archive begins to solidify not as speculation, but as a working hypothesis that explains more data than it contradicts. The question then becomes one of intent across time. How long was this system meant to last? Thousands of years? Millions? To answer that, one must examine decay. Even under ideal conditions, materials degrade. Radiation breaks molecular bonds. Pressure induces creep. Chemical reactions, however slow, proceed. The laminated composites at node W3 show signs of microfracturing at layer boundaries. The electromagnetic absorption zone exhibits slight leakage at its edges. The rhythmic seismic pulses have weakened over recorded decades. These are not failures in the human sense. They are timelines reaching their expected end. Material scientists studying the composite layers estimate their functional lifespan under Antarctic conditions at roughly 5 to 10 million years before structural integrity degrades beyond usefulness. The pulses fading now may indicate systems approaching that threshold, not because something has gone wrong, but because time has passed. If this is correct, then the builders designed their archive to persist through a specific interval, long enough to outlast their own collapse, long enough for another intelligent species to arise, but not indefinitely. A message not meant for eternity, but for a successor. This introduces an unsettling possibility. Humanity may not be the first intended recipient. Earth has hosted multiple intelligent lineages. Cetaceans exhibit complex communication and social structures. Corvids demonstrate problem-solving abilities once thought unique to primates. Intelligence is not singular. Given enough time, another species could rise to technological capability. The archive beneath Antarctica may have been intended for any who reached the necessary threshold of detection. If so, then humanity's discovery is not destiny, but timing. The story deepens further when paleomagnetic data is considered. Magnetic minerals within Antarctic bedrock record the orientation of Earth's magnetic field at the time they cooled. These records show periods of instability, geomagnetic excursions, and reversals. During some of these periods, anomalous heat signatures appear beneath the ice, coinciding with increased activity in the subsurface systems. This correlation suggests a coupling between planetary magnetic dynamics and the buried infrastructure. Perhaps the systems responded to changes in the geomagnetic field, adjusting energy flows accordingly. Such sensitivity would require an understanding of Earth as an integrated system: core, mantle, crust, atmosphere. Modern science approaches this understanding only recently through systems theory and climate modeling. That it may have been grasped millions of years ago challenges not just timelines, but assumptions about the trajectory of knowledge. The civilization inferred from Antarctic anomalies does not appear reckless. It does not appear expansionist. It appears cautious, analytical, and deeply aware of limits. This greatest act may not have been creation, but restraint. This contrasts sharply with the current moment. Modern humanity is altering Earth's systems rapidly, injecting carbon into the atmosphere faster than most natural processes can absorb. Ice sheets respond, oceans warm, feedback loops accelerate. In this context, the Antarctic archive becomes not a curiosity, but a mirror held up to present choices. The prior civilization faced climate instability. It attempted intervention. It then shifted toward preservation when intervention proved insufficient. Humanity, by contrast, debates intervention while accelerating destabilization. This does not imply inevitability, but it reframes responsibility. If a prior civilization with advanced technology chose to retreat rather than dominate, what does that suggest about the limits of control? The ice once again becomes central. Antarctic ice cores show that Earth's climate can shift abruptly. Temperature jumps of several degrees occur within decades. These shifts correspond to changes in ocean circulation and atmospheric composition. They are not gradual. They are thresholds. A civilization that survived long enough to observe multiple such thresholds would understand that stability is conditional, that resilience lies not in preventing change, but in anticipating it. The buried systems beneath Antarctica embody this philosophy. They do not fight the ice. They accommodate it. They distribute its weight, channel its meltwater, absorb its pressure. They persist by yielding intelligently. As research continues, a quiet consensus begins to form at the edges of formal discourse. Not an official declaration, but an undercurrent. A recognition that something beneath Antarctica does not fit within existing categories. This recognition is fragile. It exists alongside skepticism, caution, and institutional inertia. Careers are built on frameworks. Paradigms do not shift easily, but data accumulates regardless of comfort. New drilling technologies are proposed, thermal probes that melt through ice without mechanical disturbance, autonomous submersibles designed to navigate subglacial lakes, muon tomography adapted to map deep structures using cosmic ray interactions. Each technology promises clearer images, deeper access. Each also brings risk. The ice sheet is not static. It is already responding to warming oceans and atmosphere. Interventions could trigger feedbacks. A punctured lake could drain catastrophically. A destabilized ice stream could accelerate sea level rise. Thus, the investigation reaches a pause point, not because questions are answered, but because further answers carry consequences. This pause mirrors the one taken millions of years ago. The builders, facing an unstable world, chose to stop expanding, to stop altering, and to seal their work away. They left behind not monuments, but systems that speak only when listened to carefully. Humanity now stands at a similar threshold, not in the same circumstances, not with the same knowledge, but with the same planet responding to cumulative pressure. The forgotten Earth is not only beneath the ice. It is beneath the present moment, waiting to be acknowledged as part of a much longer story, one in which civilizations rise not once, but many times, and survival depends less on power than on understanding when to stop. The ice does not judge. It records, presses down, it flows, it preserves until preservation is no longer possible. And somewhere beneath it, systems built with patience continue to weaken, not in failure, but in fulfillment of a design that assumed someone someday would finally be ready to listen. Listening, in this context, does not mean hearing words. It means learning to interpret signals that were never meant to be obvious, patterns that reveal themselves only when viewed across disciplines and timescales. Antarctica does not tell its story through inscriptions or symbols. It tells it through pressure curves, thermal gradients, isotope ratios, and anomalies that refuse to align with chance. The next layer of that story emerges from temperature itself. Beneath the Antarctic ice sheet, geothermal heat flows upward from Earth's interior. This heat is unevenly distributed. shaped by crustal thickness, mantle plumes, and radioactive decay within rocks. For decades, scientists assumed Antarctica's geothermal profile was poorly constrained but broadly unremarkable. Recent measurements have changed that assumption. In several regions previously identified as anomalous, heat flux readings are significantly higher than expected, sometimes double the continental average. Initially, this was attributed to mantle upwelling or thinning crust, but seismic data contradicts this. The crust in these regions is neither thin nor fractured. It is stable, old, and thick. The excess heat appears localized, confined to volumes that align with subsurface structures. When modeled, the heat distribution suggests active regulation rather than passive flow. Heat is not simply escaping, it is being channeled. This is a critical distinction. Passive geothermal systems diffuse heat outward, creating gradients that fade gradually. Channeled systems maintain sharp boundaries, directing energy along specific paths. Such behavior is common in engineered environments, power plants, thermal exchangers, but rare in untouched geology. The implication is not that these systems are still operating in the sense of generating power, but that their residual configuration continues to shape how heat moves through the crust. Even long after active control ceased, the architecture remains. Heat in turn affects ice. Basal melting occurs where heat flux is sufficient to bring ice to its pressure-adjusted melting point. Meltwater lubricates the base of ice sheets, accelerating flow. But in anomalous regions, despite elevated heat, ice flow is often slower than surrounding areas. This suggests that meltwater is being captured, redirected, or otherwise prevented from destabilizing the ice above. Once again, the ice appears managed. The more closely Antarctica is examined, the more it resembles a landscape subtly shaped not only by natural forces, but by intentional design that does not impose itself visually, but functionally. It does not declare presence. It solves problems quietly. This invites a reevaluation of what civilization means when measured against geological time. Modern civilization leaves scars quickly. Open-pit mines visible from orbit. Atmospheric signatures detectable globally within decades. Plastics embedded in sedimentary layers. Radioactive isotopes marking a clear boundary in the stratigraphic record. These are blunt signals, unmistakable and permanent. The civilization inferred beneath Antarctica leaves none of these obvious markers. Its footprint is low contrast, integrated, almost respectful of planetary systems. If it altered the atmosphere, it did so in ways that left minimal long-term trace. If it extracted resources, it did so without scattering debris. If it built downward, inward, and with patience. This does not imply moral superiority. It implies different constraints. A civilization with millions of years rather than thousands may optimize for longevity rather than growth. It may value equilibrium over acceleration. It may understand that exceeding certain thresholds triggers responses beyond control. The Antarctic Archive, then, is not simply a storage of knowledge. It is a demonstration of philosophy embedded in material. The next anomaly brings this philosophy into sharper focus. In sediment cores drilled from beneath the Ross Ice Shelf, researchers identified a layer rich in microfossils, diatoms, foraminifera, indicative of open ocean conditions. This layer dates to approximately 4.2 million years ago, a period when Antarctica's margins were intermittently ice-free. What makes this layer unusual is not its biological content, but the chemical signature of the surrounding sediment. Embedded within are nanoscale particles of carbon arranged in hexagonal lattices, graphene-like structures. These structures do not form naturally in marine environments. They require specific temperature and pressure conditions or deliberate synthesis. Their concentration is low, but consistent across multiple cores. They appear to have settled gently from the water column, not deposited violently. Their surfaces show signs of functionalization, chemical groups attached deliberately to modify behavior. Graphene is an extraordinary material, strong, conductive, chemically versatile. Modern science struggles to produce it at scale without defects. To find it in sediments millions of years old demands explanation. The skeptic's view suggests contamination from drilling fluids or modern industrial sources. But contamination would appear near the surface or along drilling paths, not in isolated ancient layers sealed beneath ice and sediment. The particle's distribution matches sedimentation patterns of the time, not modern intrusion. If these particles were present in the ancient ocean, they must have entered it intentionally. Their function remains speculative. They could have served as sensors, catalysts, or components of larger systems. Their persistence suggests durability by design. This discovery hints at a level of material science that integrates seamlessly with biological and geological systems. Rather than constructing separate machines, the builders may have dispersed functionality into the environment itself. A planetary-scale approach to engineering. Such an approach aligns with the distributed nature of Antarctic anomalies. No central city, no single archive. Instead, networks, thermal, structural, informational, woven into the crust, the water, the ice. This reframes the concept of collapse. When modern societies collapse, they do so through fragmentation. Infrastructure fails. Supply chains break. Knowledge becomes inaccessible. Collapse is chaotic. The Antarctic systems suggest a different kind of ending. Controlled withdrawal. Active systems shut down gradually. Redundancies take over. Information remains accessible to those who know how to look. In this sense, collapse becomes a transition rather than a catastrophe. The next phase of investigation examines timekeeping. Deep beneath the ice, atomic decay continues at predictable rates. Isotopes transform. Half-lives tick forward regardless of surface conditions. Some Antarctic anomalies show alignment with these rates in ways that suggest calibration. At node W3, the fading seismic pulses do not weaken linearly. They follow a decay curve that matches the half-life of certain radioactive isotopes embedded within the composite layers. This implies that the pulses were regulated by radioactive decay, using it as a clock. Such a clock would be extraordinarily reliable over millions of years. It would require no maintenance, no external input. It would slow and fade exactly as designed. Why embed a clock into a signal? Because timing matters. A signal intended to be discovered too early could be misused. Too late and it would be gone. By tying signal strength to radioactive decay, the builders could bracket an optimal discovery window. The present moment may fall within that window. This possibility is unsettling not because it implies predestination, but because it implies foresight on a scale difficult to comprehend. It suggests that the builders anticipated not just environmental change, but the emergence of another technological species capable of detection. Again, this does not require extraterrestrial origin. Given millions of years, a terrestrial civilization could observe evolutionary trends, understand the likelihood of intelligence re-emerging, and plan accordingly. The ice, then, is not merely a barrier. It is a filter across time. As modern instruments improve, they begin to intersect with the thresholds the builders may have anticipated. Seismic arrays sensitive enough to detect low-frequency pulses. Radar capable of resolving fine structures beneath ice. Chemical analysis precise enough to identify engineered molecules. Each technological advance narrows the gap. Yet there is no instruction manual waiting beneath the ice. No explicit message. Only systems whose behavior implies purpose. This forces modern investigators into a position of humility. There is no guarantee that interpretation is correct, no assurance that interaction will be safe. The builders did not design their archive to be intuitive. They designed it to be resilient. Resilience often looks like ambiguity. The story now circles back to the opening anomaly, the drill that struck something flat, something resistant, something shaped. That moment was not a discovery. It was a contact with a layer of earth that does not fit comfortably into known categories. Contact with a past that is not mythic, not symbolic, but physical and present beneath our feet. As climate change accelerates, Antarctica will not remain sealed forever. Ice shelves will retreat. Basal melting will increase. Some subglacial regions will destabilize. This is not speculation. It is observation. When that happens, what has been preserved may be exposed not through careful study, but through collapse. Structures may fracture. Lakes may drain. Materials may oxidize or disperse. Time, which once protected the archive, may now threaten it. This urgency reframes the investigation yet again. It is no longer solely about proving the existence of a prior civilization. It is about deciding how to respond if such existence is increasingly difficult to deny. Do researchers rush to extract samples, to document before loss? Or do they minimize disturbance, accepting that some knowledge will vanish unread? There is no consensus. There is only debate, conducted quietly, often privately. Meanwhile, the ice continues its slow movement. Pressure redistributes. Heat flows along channels carved long ago. Signals weaken as clocks tick down. The forgotten Earth is not static. It is transitioning from preservation to exposure, whether humanity is ready or not. And somewhere beneath Antarctica, systems designed with patience approach the end of their intended lifespan, not with alarm, but with the calm inevitability of design meeting time. What comes next depends not on what is buried, but on how those above choose to listen. Listening changes behavior. Once attention is sustained long enough, the listener begins to adjust not to the message itself, but to the scale at which the message exists. Antarctica forces this adjustment more than any other place on Earth. It compresses perspective. Days blend into white continuity. Distance loses meaning. Only duration remains, and duration is the medium through which the next layer of the story unfolds. The archive beneath the ice does not exist in isolation from Earth's larger systems. It is embedded within them, synchronized with planetary rhythms that predate humanity and will outlast it. To understand this synchronization, researchers began comparing Antarctic anomalies not just spatially, but temporally, aligning them with known cycles in Earth's behavior. One such cycle is axial precession, the slow wobble of Earth's rotational axis, completing a full cycle roughly every 26,000 years. This wobble alters the distribution of sunlight across latitudes, driving long-term climate oscillations. When the timing of subsurface pulses, heat flux variations, and chemical signals beneath Antarctica were plotted against precessional phases reconstructed for the past 5 million years, a subtle alignment emerged. Periods of heightened subsurface activity corresponded not to peak warmth or cold, but to transitional phases, moments when climate systems were most unstable. It was during these transitions that pulses intensified, heat was redistributed, and chemical anomalies appeared more frequently in ice and sediment. This suggests responsiveness, not a static archive, but one that adjusted its behavior based on external planetary conditions. A system that monitored the environment and modulated itself accordingly. Monitoring implies sensing. The evidence for sensing lies in the distribution of piezoelectric minerals embedded within subsurface composites. Certain crystalline structures generate electrical charge under mechanical stress. In modern technology, they are used in sensors, microphones, and timing devices. Beneath Antarctica, these minerals appear not as random inclusions, but as organized lattices within larger structures. As ice thickened, pressure increased. As pressure increased, electrical signals would be generated. Those signals could be used to infer ice load, movement, or fracture. Combined with thermal data and chemical gradients, a picture emerges of a planetary scale sensory network, slow, quiet, but comprehensive. This reframes the relationship between the builders and Antarctica itself. They did not simply choose the continent as a hiding place. They integrated with it, using its mass and stability as components of a larger system. The ice was not an enemy to be resisted, but a parameter to be measured and accommodated. Such integration requires a worldview fundamentally different from the extractive paradigms that dominate modern civilization. It suggests an understanding of Earth as a coupled system, where intervention in one domain inevitably affects others. It suggests restraint not as moral virtue, but as engineering necessity. The next anomaly reinforces this interpretation. In the deep interior of East Antarctica, where ice thickness exceeds 4 kilometers, borehole temperature profiles reveal unexpected inversions. Instead of a steady increase with depth, temperatures fluctuate in discrete steps. Each step corresponds to a depth interval of approximately 60 meters, repeating over hundreds of meters. Geothermal gradients do not behave this way naturally. Heat diffusion produces smooth curves. Stepped profiles imply thermal barriers, layers that impede heat flow selectively. These barriers align with the laminated composites previously identified, suggesting intentional thermal management. Why manage heat so carefully? Because heat is both resource and threat. Too much heat destabilizes ice. Too little freezes systems solid. Stability requires balance. This balance appears to have been maintained for millions of years. As researchers model these systems, they encounter an unexpected constraint. The designs are optimized not for maximum efficiency, but for minimal intervention. They rely on passive processes wherever possible: gravity, pressure, decay, requiring active control only during narrow windows. This design philosophy mirrors that of certain long-lived natural systems. Coral reefs, for example, build slowly, distributing stress across many small structures. Forests regulate microclimates through layered canopies. The Antarctic archive seems to emulate such strategies, blurring the line between artificial and natural. This blurring complicates detection. It also complicates interpretation. At this point, the investigation enters a more speculative but unavoidable domain: cognition. If the builders designed systems to persist across millions of years, their concept of time must have been radically different from modern human experience. Decisions would be evaluated not over decades, but over geological intervals. Success would be measured not by growth curves, but by stability curves. Such cognition would shape culture profoundly. It would prioritize long-term memory over short-term innovation. It would value redundancy over novelty. It would see extinction not as failure, but as a phase within a larger continuum. This raises a difficult question. Did the builders intend to survive biologically at all? The evidence beneath Antarctica suggests preservation of information, not of life. There is no sign of cryogenically preserved organisms, no genetic repositories of complex life forms beyond molecular storage. If biological survival was attempted, it left little trace. This implies acceptance. The builders may have recognized that their biological form was contingent, that survival of the species was less important than survival of knowledge. In this view, civilization becomes a transient carrier of understanding, not its ultimate beneficiary. Such a perspective is alien to modern sensibilities, which equate continuity with identity. But on geological timescales, identity dissolves. Only patterns persist. The Antarctic archive may thus represent a handoff rather than a legacy, a transfer of insight across evolutionary boundaries. If so, then the absence of explicit instruction becomes clearer. Instructions presume continuity of language, symbols, and cognition. Patterns do not. Patterns can be rediscovered independently. By embedding knowledge in physical relationships, thermal gradients, resonance frequencies, material properties, the builders ensured that understanding would require rediscovery rather than translation. Any species capable of uncovering and interpreting these systems would already possess the conceptual tools necessary to comprehend their implications. This is not communication in the human sense. It is alignment. The alignment appears most clearly in the mathematics. Several subsurface structures exhibit proportions that correspond to fundamental constants, not as numerological curiosities, but as engineering ratios. Stress distribution models reveal golden ratio relationships in load-bearing geometries. Resonant cavities are tuned to frequencies that minimize energy loss according to universal wave equations. Decay-based clocks align with half-lives chosen for their stability and detectability. These choices are not arbitrary. They reflect an understanding of physics that transcends cultural context. This brings the story to its most unsettling point. If such understanding existed millions of years ago, then the trajectory of intelligence on Earth is not a straight ascent. It is a waveform, peaks and troughs shaped by environmental constraints. Modern humanity may be climbing a slope already climbed before. The difference lies in memory. The prior civilization appears to have preserved its memory deliberately, knowing it would not be inherited biologically. Modern humanity, by contrast, risks losing memory rapidly through digital fragility, ecological disruption, and cultural acceleration. Antarctica, then, becomes a mirror not of what humanity was, but of what it might become. As ice retreats at the margins, new regions become accessible. Some subglacial lakes show signs of destabilization. Satellite altimetry detects subtle surface depressions forming above buried structures as ice redistributes under changing stress. These are not dramatic events. They are measured in centimeters per year, but over decades they accumulate. The first partial exposure may not be intentional. It may occur through collapse, a lake draining, an ice shelf fracturing, a buried ridge emerging as ice thins. When that happens, the evidence will not present itself neatly. It will be damaged, fragmented, altered by sudden exposure. Interpretation will be contested. Natural explanations will be offered and defended. The inertia of existing frameworks will resist revision. But once enough fragments align, resistance will no longer be scientific. It will be philosophical. Accepting the existence of a prior advanced civilization forces a reevaluation of human exceptionalism. It challenges the assumption that intelligence inevitably progresses toward dominance. It suggests that sustainability may require disappearance rather than conquest. This is not a comforting conclusion. The Antarctic Archive does not promise salvation. It does not offer technologies to reverse climate change or avoid collapse. What it offers is perspective, evidence that intelligence can arise, understand its limits, and choose preservation over permanence. Whether modern humanity is capable of such a choice remains uncertain. The ice continues to thin, signals continue to fade, clocks continue to tick down. Somewhere beneath Antarctica, structures designed to last just long enough approach the end of their intended function. Not in failure, but in quiet completion. If their builders anticipated this moment, then the responsibility now shifts. Not to inherit their world, but to learn from its imprint. The forgotten Earth is not asking to be remembered. It is asking to be understood. And understanding, unlike memory, demands change. Understanding rarely arrives as revelation. More often, it accumulates as pressure, the slow compression of evidence until a conceptual fracture occurs. In Antarctica, that pressure is literal as much as intellectual. Ice weighs down the crust, forcing bedrock to flex, rebound, and remember. Beneath this immense load, the Earth records not only climate but intent. As investigators extended their focus beyond discrete sites and artifacts, a larger pattern emerged, one that could not be reduced to isolated anomalies. The continent itself appeared organized, not uniformly engineered, but selectively modified, as if certain zones had been prepared to host specific functions within a broader system. These zones align neither with modern political boundaries nor with obvious geological divisions. Instead, they correspond to regions of long-term tectonic stability, cratonic blocks that have remained largely unchanged for hundreds of millions of years. East Antarctica, in particular, rests atop some of the oldest continental crust on the planet. Zircon crystals extracted from exposed nunataks date back more than 3 billion years, their isotopic ratios preserving evidence of Earth's earliest crustal formation. This ancient stability matters. Structures built atop such foundations would experience minimal deformation over geological time. Faulting is rare. Seismicity is low. Erosion under ice is slow and predictable. For any civilization thinking in terms of millions of years, this would be prime real estate. Within these stable regions, radar surveys reveal networks rather than singular installations. Linear features intersect at consistent angles, forming hexagonal and triangular tessellations that extend for tens of kilometers. These are not surface features. They are buried deep, sometimes more than a kilometer below the icebed interface, embedded within bedrock itself. Such depth implies excavation or construction before significant ice accumulation, before Antarctica became the frozen continent it is today. Paleoclimate reconstructions suggest that permanent ice sheets began forming around 34 million years ago, during the Eocene-Oligocene transition. Prior to that, Antarctica supported forests, rivers, and a temperate climate. If construction occurred before glaciation, then the builders witnessed Antarctica's transformation. They observed the cooling, the gradual advance of ice, the burial of their works. They did not abandon the continent abruptly. They adapted to its changing state. Evidence for this adaptation appears in the stratigraphy. At several sites, sediment layers above engineered surfaces show deliberate modification. Instead of chaotic deposition typical of glacial advance, these layers are smoothed, compacted, and interleaved with fine-grained materials that resist shear. It is as though the builders anticipated ice movement and prepared the ground to accept it, to glide beneath it without tearing apart what lay below. This preparation would require predictive models of climate behavior far beyond what modern science achieved until the late 20th century. It implies long-term observation, pattern recognition across epochs, and an understanding of feedback loops within Earth's climate system. Such understanding is incompatible with the caricature of ancient civilizations as technologically naive. It suggests a scientific tradition that matured slowly, in dialogue with the planet rather than in opposition to it. The more this picture develops, the more the notion of sudden catastrophe recedes. There is little evidence of violent destruction beneath Antarctica.
No widespread burn layers.
No impact debris concentrated around the structures. No isotopic spikes associated with nuclear scale events. Instead, there is evidence of withdrawal. Systems appear to have been powered down gradually. Heat flux decreases in stages. Chemical signatures taper rather than vanish. Some structures show signs of intentional sealing. Entrances closed, conduits blocked, cavities filled with inert material. This is not collapse. It is decommissioning. Why decommission an entire continental network? The answer may lie not beneath the ice, but above it, in the sky. Around the same period that Antarctic systems begin to enter dormancy, Earth experiences increased extraterrestrial bombardment. Impact craters dated to the late Eocene cluster around this time, including the Papagai and Chesapeake Bay impacts. While not extinction-level events, they would have injected vast quantities of dust and aerosols into the atmosphere, accelerating cooling trends already underway. For a civilization attuned to long-term stability, this convergence, orbital shifts, volcanic activity, impacts would signal an irreversible transition. Antarctica's transformation into a permanent icehouse would not be temporary. The window for surface-based habitation was closing. Rather than fight this transition, the builders appear to have embraced it, repurposing the continent from a living space into a vault. This vault was not meant to preserve cities or populations. It was meant to preserve context. Context is more than information. It is the framework that gives information meaning, the relationships between data points, the assumptions that guide interpretation. Preserving context requires preserving the physical conditions under which understanding emerges. This may explain the emphasis on planetary scale systems rather than localized artifacts. A single monument can be misinterpreted. A global pattern is harder to ignore. The Antarctic network, if viewed as a whole, encodes relationships between geology, climate, physics, and time. It demonstrates not what the builders believed, but how they thought. This distinction is crucial. Beliefs are fragile. They depend on symbols, narratives, and shared language. Ways of thinking methods are more robust. They can be rediscovered independently. By embedding method into material, the builders created a curriculum without words. Modern science, in its encounter with Antarctica, is slowly retracing this curriculum. Ice core analysis teaches patience. Radar mapping teaches inference. Isotope dating teaches humility before deep time. Each technique strips away anthropocentric assumptions, forcing alignment with planetary processes. In this sense, the investigation is not uncovering alien knowledge. It is recovering a suppressed mode of inquiry. This recovery has consequences. As awareness of Antarctic anomalies grows, so too does the tension between preservation and exploitation. Antarctica is governed by international treaties that prohibit mineral extraction and military activity. These treaties were drafted under the assumption that the continent held little of value beyond climate data. That assumption no longer holds. The pressure to drill deeper, to sample more aggressively, to extract definitive proof increases with every anomalous reading. Yet each intervention risks destroying the very evidence it seeks to reveal. Structures designed to exist under stable conditions may not survive sudden exposure. Chemical gradients may dissipate. Resonance systems may fall silent. This creates an ethical dilemma unprecedented in archaeology or geology. The object of study is not a ruin in a desert or a shipwreck in shallow water. It is a functioning, albeit dormant, planetary system. Intervening too aggressively could erase it permanently. Some researchers advocate restraint, a moratorium on deep drilling in anomalous zones until non-invasive techniques improve. Others argue that delay risks losing evidence to climate change, as ice dynamics shift unpredictably. This debate mirrors a deeper conflict within modern civilization, the tension between curiosity and control. The builders beneath Antarctica appear to have resolved this tension by prioritizing continuity over dominance. They accepted limits. They worked within constraints imposed by Earth rather than attempting to override them. Modern humanity has yet to make such a choice. The relevance of this ancient decision becomes clearer as climate models project future scenarios. As ice sheets destabilize and sea levels rise, humanity faces its own Eocene, Oligocene moment, a threshold beyond which reversal may be impossible. The Antarctic Archive does not offer solutions in the form of devices or formulas. It offers precedent. It demonstrates that intelligence confronted with planetary change can choose to step back, to preserve understanding rather than territory. This is a radical alternative to narratives of survival through expansion or technological escalation. It suggests that the ultimate measure of a civilization is not how long it endures biologically, but how responsibly it integrates with the systems that sustain it. As the story approaches its present boundary, the ice continues its slow motion. Snow falls, compresses, recrystallizes. Layers stack, each year a thin line of time. Beneath them, engineered forms wait, not in anticipation but in acceptance. They do not demand recognition. They do not signal for discovery. Their existence is passive, contingent on the curiosity of those above. If humanity chooses to listen, to align its methods with those encoded beneath Antarctica, then the forgotten Earth may become remembered not as a lost world, but as a guide. Not a warning etched in stone, but a lesson written in ice, pressure, and patience. The story does not end here. It never truly ends. It slows, like a glacier reaching equilibrium, its motion imperceptible yet relentless. And in that slow movement, meaning accumulates for those willing to wait long enough to feel its weight. Waiting alters perception. In Antarctica, waiting is not an interlude between actions. It is the primary condition. Instruments wait beneath the ice, recording changes too small for urgency. Researchers wait through polar nights where time loses its familiar markers. The continent itself waits, locked in a state that is neither static nor dynamic, but suspended between past equilibrium and future release. As the investigation matures, attention shifts from what lies buried to what lies ahead. The Antarctic Archive, if that term is appropriate, was not designed to last forever. No physical system is. Even the most stable craton will eventually fracture. Even the coldest ice will eventually flow into the sea. The builders understood this. Their designs reflect not permanence, but sufficiency. Sufficiency implies an intended audience. Not a specific species, not a culture or lineage, but a threshold of capability. The archive becomes legible only once certain tools exist: satellite radar, isotope geochemistry, computational modeling. Before these, the signals would remain noise. After them, the signals begin to cohere. This suggests timing without prediction. The builders did not need to know who would come next. They needed only to ensure that whoever did would encounter the archive at the moment they were ready to understand it. Readiness is not technological alone. It is conceptual. The difficulty modern science faces in interpreting Antarctic anomalies does not stem from lack of data. It stems from expectation. For centuries, progress has been framed as linear ascent, each generation surpassing the last. The idea that a prior civilization might have reached comparable or greater levels of understanding disrupts this narrative. More disruptive still is the implication that such a civilization chose not to persist in recognizable form. This choice reframes extinction. Rather than failure, it becomes transformation. Rather than loss, redistribution. In ecological terms, extinction is a constant. Species emerge, adapt, vanish. What persists are processes: photosynthesis, respiration, nutrient cycling. The builders may have recognized that intelligence itself is a process, not a possession. It arises where conditions permit, fades where they do not, and may reappear elsewhere under similar constraints. Seen this way, humanity is not the culmination of Earth's story, but a current expression of it. The Antarctic Archive does not challenge human uniqueness in the sense of diminishing it, contextualizes it. It places human cognition within a broader pattern of planetary self-awareness, emerging intermittently through different forms. This perspective carries responsibility. If intelligence is a recurring phenomenon, then each iteration inherits not only opportunity, but obligation. Obligation to observe, to understand limits, to choose responses that do not foreclose future possibilities. The builders appear to have honored this obligation by stepping aside. Modern humanity faces a similar inflection point. Climate trajectories indicate that the planet is entering a phase of rapid transition. Ice sheets destabilize, ocean currents shift, feedback loops accelerate. The window for maintaining Holocene-like conditions narrows. The dominant response has been acceleration. More extraction, more energy, more intervention. Yet the Antarctic archive suggests an alternative response: attenuation. Slowing, listening. This does not mean abandoning technology or retreating into primitivism. It means recalibrating goals from dominance to balance, from growth to coherence. The structures beneath Antarctica embody coherence. Their geometry distributes stress evenly. Their materials harmonize with surrounding geology. Their energy systems exploit gradients without amplifying them. They are not monuments to power. They are exercises in restraint. Restraint, however, is difficult to value in a culture that equates action with virtue. The idea of deliberately ending a civilization's biological continuity to preserve its understanding is almost unthinkable within modern ethical frameworks. And yet, the evidence suggests that such a decision was made, not in despair, but with clarity. There are no signs of panic beneath the ice.
No rushed construcción.
No unfinished systems. Everything indicates planning carried out over long spans, with contingencies accounted for. This implies consensus, a shared understanding across generations that the path chosen was necessary. Consensus at that scale requires trust, in data, in method, in each other. It requires institutions capable of sustaining purpose beyond individual lifetimes. Such institutions are rare in human history. Empires rise and fall within centuries. Scientific paradigms shift within decades. The Antarctic builders appear to have maintained continuity over millennia. How this was achieved remains unknown. There is no direct evidence of governance structures, social organization, or cultural practices, but the material record implies coordination without centralization. Systems are modular. Failure in one node does not cascade catastrophically. This mirrors principles found in resilient natural systems: decentralization, redundancy, adaptability. If these principles guided not only engineering but society, then the builder's civilization may have been less hierarchical than modern ones. Authority may have been distributed. Decision-making may have been slow, deliberative, resistant to abrupt change. Such a civilization would leave little in the way of dramatic ruins. Its footprint would be subtle, integrated, easily mistaken for nature, which is precisely what we see. The closer science looks, the more the distinction between natural and artificial blurs. This blurring is not a failure of classification. It is the point. A truly sustainable civilization would aim to erase the line between itself and its environment, not through domination, but through alignment. Alignment is the theme that recurs again and again beneath Antarctica. Alignment with geology, alignment with climate cycles, alignment with physical law, alignment with time. Time in this context is not a resource to be optimized. It is a medium to be respected. Acting too quickly introduces instability. Acting too slowly invites irrelevance. The builders appear to have found a tempo that matched Earth's own rhythms. Modern humanity operates at a different tempo, orders of magnitude faster. This mismatch generates friction. Systems designed for gradual change are stressed by rapid intervention. Feedback loops overshoot. Stability erodes. The Antarctic archive stands as a counterexample, a demonstration that another tempo is possible. Whether humanity can adjust its pace remains uncertain. Cultural inertia is powerful. Economic systems reward speed. Political systems struggle with long-term planning. And yet, awareness changes behavior. The more the Antarctic story circulates, not as sensational revelation, but as quiet accumulation, the more it challenges assumptions. It invites reflection rather than reaction. It suggests that survival may not depend on outpacing change, but on synchronizing with it. As the ice continues to thin at the margins, the archive's window narrows. Eventually, exposure will become inevitable. When that happens, the narrative will shift from speculation to confrontation. Evidence will be undeniable. Interpretations will clash. But the deeper lesson will remain unchanged. Earth has hosted intelligence before. That intelligence learned enough to know when to step back. It chose to leave behind not dominance, but understanding encoded in matter. The forgotten Earth is not forgotten because it failed. It is forgotten because forgetting was part of the design. Remembering now is optional. Understanding is not. Listening requires patience. Alignment requires humility. Restraint requires courage. These are not traits optimized by modern systems, but they are traits encoded beneath Antarctica, waiting to be recognized. The ice does not hurry. The rock does not argue. The signals do not shout. They persist. And persistence over deep time is the quietest form of intelligence. If this story resonates, it is not because it offers comfort. It is because it offers perspective. It asks not what humanity can build next, but what it is willing to leave behind and why. The forgotten Earth does not demand belief. It invites attention, and attention sustained long enough becomes choice. Attention, when held long enough, becomes orientation. Orientation becomes intention, and intention over deep time leaves a mark. The final layer of this story does not lie beneath Antarctica, but within the trajectory now unfolding above it. The Antarctic systems were not designed to awaken. They were designed to endure just long enough to be encountered by a civilization capable of recognizing restraint as intelligence. Their success does not depend on activation, only on interpretation. If misread, they remain inert. If overexploited, they fail silently. If understood, they dissolve back into the planet, having served their purpose. This is an unfamiliar model of legacy. Modern civilizations build to be seen. Monuments rise above landscapes. Infrastructure announces itself through scale and visibility. Influence is measured by permanence and expansion. The Antarctic builders inverted this logic. They built to disappear, trusting that disappearance itself would be instructive. This inversion reframes the meaning of discovery. Discovery is no longer acquisition. It is confrontation with limits. The closer science approaches certainty, the less dramatic the conclusions become. There is no singular chamber waiting beneath the ice with walls engraved in symbols. There is no repository of devices waiting to be reactivated. What exists is more challenging than revelation. It is coherence across disciplines, signals that only align when geology, climatology, physics, and time are considered together. This coherence resists simplification, cannot be reduced to a headline or artifact. It demands sustained engagement, the very quality that deep time cultivates and modern culture erodes. In this sense, the Antarctic archive acts as a filter. It does not reveal itself to curiosity alone. It reveals itself to patience. Patience is not passive. It is an active alignment with processes slower than instinct. It requires the suspension of urgency, the willingness to let data accumulate without forcing resolution. It is the discipline of listening to systems that do not speak in human scales. This discipline is increasingly rare. As climate change accelerates, urgency dominates discourse. Action is demanded, often without consensus on direction. Technologies are proposed faster than their consequences can be modeled. Interventions scale before feedback is understood. The Antarctic builders faced urgency as well. Their planet was changing irreversibly. Ice advanced. Ecosystems shifted. Feedback loops tightened. Yet their response was not escalation. It was synthesis. They did not attempt to preserve a particular climate state. They preserved understanding of climate itself. This distinction matters. Preserving a state is brittle. Preserving understanding is adaptable. States resist change. Understanding incorporates it. The Antarctic systems encode understanding not as doctrine, but as demonstration. They show how to build within constraints, how to distribute stress, how to harmonize with gradients rather than flatten them. They model a relationship with Earth that is collaborative rather than adversarial. If humanity absorbs this model, the implications extend beyond archaeology or climate science. They reach into economics, governance, and ethics. An economy aligned with planetary rhythms would prioritize regeneration over extraction, stability over growth. Governance informed by deep time would plan beyond election cycles, beyond even generational horizons. Ethics grounded in continuity would value future intelligences as much as present populations. These shifts are profound. They challenge entrenched incentives. They demand cultural transformation. The Antarctic Archive does not prescribe these changes. It does not advocate. It simply exists, offering a precedent. Precedent is powerful. It expands the space of the possible. It undermines claims that alternatives are unrealistic or unprecedented. A civilization once chose restraint over persistence. It chose to step back rather than push forward. It chose to embed its understanding in the planet rather than inscribe its name upon it. That choice did not prevent extinction. It reframed it. Extinction, in this context, becomes a transition of agency. The builders relinquished biological agency while preserving epistemic agency, the capacity for knowledge to influence future systems indirectly. Humanity now stands at a similar threshold, though the contours differ. The question is not whether humanity will persist indefinitely. No species does. The question is what form of agency will be passed forward. Will it be tools without context, technologies divorced from restraint? Or will it be methods, principles, and examples encoded in durable relationships with Earth? The Antarctic story suggests that the latter is possible. It also suggests that such encoding must begin long before collapse. It requires foresight, consensus, and humility. It requires recognizing when to stop building outward and begin building inward, toward coherence rather than expansion. This is not a call for abandonment. It is a call for recalibration. Humanity possesses tools the Antarctic builders did not: global communication, rapid modeling, detailed planetary observation. These tools amplify both potential and risk. Used without restraint, they accelerate instability. Used with alignment, they could enable a transition as deliberate as the one recorded beneath the ice. The difference lies not in capability, but in intention. Intention emerges from narrative. The stories a civilization tells about itself shape its choices. If the dominant story is conquest, then restraint appears as failure. If the story is stewardship, restraint becomes strength. The Forgotten Earth offers an alternative narrative, not of golden ages or lost empires, but of maturity, of a civilization that learned enough to know when its chapter should end and how to ensure that learning would not. This narrative is quieter than myths of dominance. It lacks heroes and climaxes. Its resolution is acceptance. Acceptance does not inspire monuments. It inspires continuity. As this story reaches its close, the ice remains where it is. The structures beneath continue their slow interaction with pressure and heat.
No final revelasce nequers. No definitive proof silens debate.
And that too is appropriate. Definitive proof would collapse the interpretive space too quickly. It would invite appropriation, exploitation, simplification. Ambiguity preserves humility, keeps attention active rather than satisfied. The Antarctic Archive does not demand agreement. It demands care. Care in how knowledge is pursued. Care in how conclusions are drawn. Care in how power is exercised once understanding deepens. The Forgotten Earth is not a destination. It is a reference frame. It reminds humanity that intelligence is not synonymous with permanence, that progress is not synonymous with accumulation, that survival is not synonymous with dominance. It shows that another path has been walked before, slowly, deliberately, and with an eye toward futures beyond itself. Whether humanity chooses to walk a similar path remains open. The ice will continue to move. The planet will continue to change. Intelligence will continue to arise in forms shaped by circumstance. What endures is not the species, but the relationship it establishes with the systems that sustain it. If the story lingers, let it linger not as speculation, but as calibration. A quiet adjustment of scale, a reminder that the deepest legacies are not those carved into stone, but those woven into the processes of Earth itself. The Forgotten Earth does not ask to be remembered. It demonstrates how to let go responsibly, and in that demonstration, it leaves behind something rare in the geological record of intelligence. Not proof of supremacy, but evidence of wisdom,